Imagine you own a building that never sleeps. Not a factory, not an office, not a warehouse. A building where the product being made is invisible, the customers never visit, and the demand never stops. Not at midnight, not on Christmas, not during a hurricane. Every email you have ever sent passed through a building like this. Every streaming video, every online transaction, every search query, every artificial intelligence response. All of it lives somewhere physical. All of it requires power, cooling, physical space, and someone who owns the building that contains it. On the surface, a data center looks like the most boring real estate investment in the world, a giant concrete box full of humming machines. From the inside, it is one of the most capital-intensive, technically complex, and strategically critical infrastructure businesses in the modern economy. And the part that almost nobody outside the industry understands is this: the servers, the computers, the hardware, the machines are not what you are selling. You are selling power and cold air. Here is the economics of owning a data center. Let's start with the number that redefines what the word expensive means. Building a hyperscale data center, the kind that powers cloud computing at meaningful scale, costs between $1 billion and $10 billion depending on size, location, and power infrastructure requirements. A single hyperscale campus developed by Amazon Web Services, Microsoft Azure, or Google Cloud can consume more than $5 billion in capital expenditure before a single server is switched on. Microsoft announced $80 billion in global data center investment for fiscal year 2025 alone. That is not a typo. $80 billion in a single year from a single company. But hyperscale is only one end of the market. A mid-tier colocation data center, the kind that houses servers for multiple enterprise customers, costs between $50 million and $500 million to develop depending on power capacity and location. The single most important variable in data center construction cost is not the building. It is the power. A data center is fundamentally a power delivery and thermal management system that happens to have servers inside it. Power infrastructure, the substations, the transformers, the uninterruptible power supplies, the backup generators, typically represents 30 to 40% of total construction cost. A facility designed to deliver 100 megawatts of IT load requires an electrical infrastructure capable of handling significantly more than 100 megawatts of raw power input, because every watt delivered to a server generates heat that must be removed, and the cooling systems that remove that heat consume power of their own. The ratio of total power consumed by a facility to the power actually delivered to computing equipment is called power usage effectiveness, PUE. A PUE of 1.0 would mean perfect efficiency. Every watt consumed goes directly to computing. A PUE of 2.0 means the facility consumes twice as much power as its servers actually use. Half of all power consumed goes to cooling, lighting, and infrastructure overhead. The industry average PUE sits around 1.5. The most efficient hyperscale facilities, built by Google and Microsoft with advanced cooling systems, achieve PUE figures below 1.2. That efficiency gap is not an engineering detail. It is a competitive cost advantage worth tens of millions of dollars per year at scale. Then there is the location problem. Data centers need three things that are increasingly difficult to find simultaneously: abundant, cheap power, physical connectivity to fiber networks, and sufficient land for the facility footprint and its cooling infrastructure. Northern Virginia, specifically Loudoun County, has become the largest data center market in the world, handling an estimated 35% of global internet traffic, precisely because it sits at the intersection of abundant power, dense fiber connectivity, and proximity to the U.S. government and financial services industries. But the concentration of data center development in Northern Virginia has created its own crisis. Power availability has become so constrained that Dominion Energy, the regional utility, has imposed multi-year queues on new power connections. Some data center developers are waiting 5 to 7 years for power delivery. That queue is not a planning problem. It is a market structure problem that is reshaping where data centers can be built and how much they cost to develop. The data center industry has three primary business models, and understanding which one you are operating is fundamental to understanding the economics. The first model is colocation. A colocation facility, colo in industry terminology, owns the building, the power infrastructure, the cooling systems, and the physical security. Customers bring their own servers and networking equipment, install it in standardized rack space, and pay the colo operator for power, cooling, and connectivity. Colocation revenue is priced in one of two ways. Power-based pricing. Customers pay per kilowatt of power capacity reserved, regardless of how much they actually consume. Space-based pricing. Customers pay per cabinet or per square foot of raised floor space, with power charges added separately. Power-based pricing has become the dominant model at scale because power is the true scarce resource in a data center, and pricing against power aligns the operator's revenue with their actual cost structure. A colocation operator charging $150 per kilowatt per month on a 50 megawatt facility, assuming full occupancy, generates $7.5 million per month, or $90 million per year in recurring contracted revenue. That revenue is highly predictable, highly sticky, and backed by long-term contracts, typically running 3 to 10 years. Customers who have installed physical infrastructure in a colocation facility, cables, custom power configurations, cross-connects to other customers, face an extraordinarily high switching cost. Migrating a data center installation is not like changing a software subscription. It is a multi-month, multi-million-dollar physical operation that risks service disruption. This creates a customer retention dynamic that the data center industry enjoys unlike almost any other infrastructure business. The second model is wholesale. A wholesale data center operator builds large blocks of capacity, typically 10 megawatts or more, and leases them to a single tenant, usually a hyperscale cloud provider, under long-term agreements of 10 to 15 years. The tenant builds out the interior, installs their own cooling systems, their own power distribution, their own servers, while the landlord provides the shell, the power connection, and the land. Wholesale rents are significantly lower per kilowatt than colocation rates because the tenant is bearing more of the fit-out cost and taking a larger long-term commitment, but the scale is dramatically larger. A single wholesale lease to Amazon Web Services for a 100-megawatt campus can generate hundreds of millions of dollars in contracted revenue over its term. The third model is hyperscale owner-operator. Amazon, Microsoft, Google, and Meta build and own their own data centers designed entirely around their proprietary hardware configurations and software architectures. These facilities are not available to external customers. They exist purely to support the cloud and consumer services of the parent company. The economics of this model are driven by the cloud services revenue, not by the data center itself. Here's the number that data center operators think about every single day: power cost per kilowatt hour. A data center consuming 100 megawatts of power continuously, 24 hours a day, 365 days a year, consumes approximately 876,000 megawatt hours of electricity annually. At an average commercial power price of 7 cents per kilowatt hour, which is achievable in low-cost power markets like Texas, the Pacific Northwest, or the Nordic countries, that annual electricity bill runs to approximately $61 million. At a power price of 12 cents per kilowatt hour, more typical of markets like Northern Virginia or the Northeast United States, the same facility spends $105 million on power annually. The difference between those two power prices, $44 million per year on a single 100 megawatt facility, is not a rounding error. It is the difference between a profitable business and a marginal one. This is why data center location decisions are fundamentally driven by power economics, and why markets with access to cheap, renewable energy have become intensely competitive battlegrounds for data center development. Iceland, with its abundant geothermal and hydroelectric power, has attracted significant data center investment from European operators seeking low-cost, low-carbon electricity. The Columbia River Corridor in the Pacific Northwest, home to massive hydroelectric infrastructure, powers a significant concentration of data center capacity for Microsoft, Google, and Amazon. Texas, with its deregulated electricity market and abundant wind generation, has attracted aggressive data center development, but also demonstrated the fragility of power-dependent infrastructure during the February 2021 grid failure that left millions without power. A data center operator in Texas during that event faced a critical choice: run backup diesel generators at enormous cost, or shut down customer systems, with all the contractual and reputational consequences that entails. The backup generator infrastructure that prevents that choice costs between $500,000 and $2 million per megawatt of capacity to install and maintain, and the diesel fuel to run it at full load for 48 hours on a 100 megawatt facility costs approximately $1 million. That is the insurance premium for operating in a market where grid reliability cannot be guaranteed. Section 4. The hyperscaler dependency. Let's talk about the dynamic that defines the economics of the data center industry at scale. The hyperscalers, Amazon Web Services, Microsoft Azure, Google Cloud, and Meta, represent the largest and fastest growing source of demand for data center capacity in the world. AWS alone operates an estimated 2 million servers globally and adds capacity at a pace that requires billions of dollars of new data center investment every quarter. For a data center developer, landing a hyperscaler as a tenant is the definition of business success. A 10-year wholesale lease to Microsoft Azure on a 200 megawatt campus provides contracted revenue visibility that supports billion-dollar financing packages and near-certain debt service coverage. But the hyperscaler relationship comes with structural risks that operators underestimate at their peril. The first risk is concentration. A wholesale operator whose revenue is 70% dependent on a single hyperscaler tenant has built a business whose financial health is entirely subordinate to the strategic decisions of one customer. When Amazon Web Services decided in 2022 to slow its capacity expansion in response to post-pandemic demand normalization, the data center operators who had over-indexed to AWS exposure faced sudden pipeline uncertainty that directly impacted their development programs and stock prices. The second risk is lease renewal. Hyperscalers negotiate their initial leases with long tenors, 10 to 15 years. But at renewal, the balance of power shifts. A hyperscaler renewing a 200 megawatt lease knows that the operator has built a facility specifically sized and configured for that tenant's requirements. Redeploying that capacity to alternative tenants is not simple. The renewal negotiation therefore occurs with the hyperscaler holding significant leverage, and renewal rates are frequently lower than initial rates as a result. The third risk is build-to-suit substitution. As hyperscalers have grown in scale and sophistication, they have increasingly chosen to own rather than lease their data center infrastructure. Amazon, Microsoft, and Google now own a significant and growing proportion of their global data center footprint. Every megawatt of capacity that a hyperscaler brings in-house is a megawatt that does not flow to independent operators. To understand what data center ownership looks like at its most successful, look at Equinix. Founded in 1998 at the height of the dot-com boom, Equinix began as an operator of neutral internet exchange points, facilities where multiple networks could connect and exchange traffic directly. That neutrality, the fact that Equinix did not favor any single network operator or cloud provider, became the foundation of its competitive moat. Today, Equinix operates 260 data centers across 72 cities and 33 countries. It generated $8.2 billion in revenue in 2023. It is structured as a real estate investment trust, a REIT, which requires it to distribute 90% of taxable income to shareholders but provides significant tax advantages on real estate holdings. The Equinix model is built around what the company calls interconnection, the ability for customers within the same facility to connect directly to each other, to cloud providers, and to networks without their traffic ever leaving the building. A financial services firm that co-locates in an Equinix facility in New York gains direct, low-latency connections to every major cloud provider, every major network carrier, and potentially thousands of other Equinix customers, all within the same physical building. That interconnection value, which Equinix charges for separately through cross-connect fees of $500 to $1,000 per connection per month, is what makes the Equinix model genuinely defensible. You cannot replicate the interconnection density of an Equinix facility by building a new data center next door. The value is in the concentration of customers who are already there. It is a network effect embedded in physical infrastructure. Equinix's revenue per cabinet, a key industry metric, runs significantly above the industry average precisely because its interconnection density commands premium pricing that pure power and space operators cannot achieve. Let's talk about what runs underneath the revenue. Power is the largest single operating cost, as already established, but the management of power costs is more complex than simply paying an electricity bill. Most large data center operators enter into power purchase agreements, long-term contracts to buy electricity directly from renewable energy generators at fixed prices. A PPA locks in a known power cost for 10 to 20 years, providing the cost predictability that data center economics require. But PPAs introduce their own risk. If market power prices fall below the PPA strike price, as happened in some markets following the natural gas price collapse of 2019, the data center operator is locked into above-market power costs that compress margin. The second major cost is maintenance and refresh. Data center infrastructure, cooling systems, power distribution equipment, UPS systems, generators, has defined service lives and requires systematic replacement. A major cooling system failure in an operating data center is not an inconvenience. It is a potential service disruption affecting hundreds of customers, triggering contractual penalty clauses and reputational damage that can take years to recover from. The third major cost is connectivity. A data center without fiber connectivity is worthless. Operators pay significant recurring fees for fiber connections to internet exchange points, to carrier networks, and to cloud on-ramps. The dedicated connections to AWS, Azure, and Google Cloud that enterprise customers require. A well-connected facility in a primary market might spend $5 million to $15 million per year on connectivity costs alone. The fourth major cost is physical security and compliance.
Data centers housing enterprise and government customers must meet rigorous physical security standards, biometric access controls, man-trap entry systems, 24-hour security staffing, and comprehensive surveillance systems. For facilities seeking government contracts, the most lucrative and stable customer segment in the industry, achieving FedRAMP, FISMA, or IL4 and IL5 compliance certifications requires significant investment in both physical infrastructure and operational processes. And then there is the property tax reality. Data centers are among the most intensely capital-employed real estate assets in existence, and many jurisdictions have historically assessed property taxes on the value of the equipment inside them, as well as the real estate itself. Several U.S. states have introduced data center tax incentives, exempting equipment from sales tax, offering property tax abatements specifically to attract development. Virginia's data center tax exemption program is estimated to cost the state over $1 billion per year in foregone revenue, a figure that has generated significant political controversy as the scale of data center concentration in Northern Virginia has become apparent. So does owning a data center actually work as a business? The answer is, it depends entirely on power access, location, and whether you understand that you are not in the real estate business. You are in the power delivery business, with a building around it. In the optimistic scenario, you secured land and power commitments in a supply-constrained market before the current demand wave made both scarce and expensive. Your facility is fully leased on long-term contracts to investment-grade tenants. Your power costs are locked through PPAs at rates that preserve healthy operating margins. Your interconnection density is high enough to command premium colocation pricing that pure wholesale operators cannot match. And the secular demand tailwinds driving your business, cloud migration, artificial intelligence infrastructure build-out, edge computing deployment, and the digitization of every industry show no sign of abating. Global data center capacity is projected to double between 2023 and 2030. Artificial intelligence training workloads alone are driving a step change in power density requirements, with AI-optimized facilities requiring 5 to 10 times the power per rack of conventional compute infrastructure. The investment banks, the infrastructure funds, and the sovereign wealth funds pouring capital into data center development are not wrong about the direction of demand. In the realistic bad scenario, you committed to development in a market where power delivery has been delayed by utility queue backlogs, where construction costs inflated 30% during the development period, and where a hyperscaler that represented 60% of your anticipated lease-up has decided to build its own facility on land 3 miles away. Your debt service clock is running, your facility is 40% leased, and the power costs you are paying on the occupied portion are being partially passed through to tenants under lease structures that cap your recovery at levels negotiated before the current inflationary environment. The AI infrastructure boom has created a gold rush mentality in data center development, and gold rushes historically produce more losers than winners among those who mine for the gold, rather than those who sell the picks and shovels. The utility companies selling the power, the cooling technology manufacturers, the fiber network operators, the construction firms building the facilities. These are the businesses that profit regardless of which data center operator wins and which loses. A data center looks from the outside like a nondescript concrete building with no windows and a lot of air conditioning units on the roof. From the inside, it is the physical foundation of the digital economy, a $300 billion global industry growing at 15% per year, consuming an estimated 2% of global electricity production today, and projected to consume 5% by 2030. The question is not whether the world needs more data centers. The world clearly does. The question is whether you can secure the power, the land, the financing, and the customers in that order before someone else does. Because in the data center business, the constraint was never capital. It was always the thing that makes the machines run. And right now, there is not enough of it.